Recording is rolling. It is Wednesday, April 23rd. So we're going to do relativity puzzles today. That's this page, which is the back side of the page that you guys were focused on yesterday. You guys were here yesterday solving the cogwheel puzzle. Most of you guys finished just by the end of class, but not then. Well, you saw the paper, so still going to work with that. You guys were trying to figure out, the opposite of what Fizeau was figuring out. Fizeau knew how fast he was spinning his cogwheel. That's an angular velocity. Therefore, he was calculating the speed of light. I told you what the speed of light was, which is safe for everybody. I gave you guys different distances to this mirror. So how fast would you have to spin your cogwheel with some number of teeth of this whole process? And that was yesterday's adventure. If you flip the page over, there's a bunch of relativity puzzles. So here, I'll walk you guys through all of these today. Most of you guys will probably finish this by the end of the class today. Guys, if you finish all the puzzles, both sides of the paper, by the end of the class today, go ahead and turn this into the grade tray. I'll start putting the scores into the grade book. You guys know tomorrow the grading period closes, and then teachers have to have grades uploaded into the grade book for the interim by the end of the weekend. So if you don't finish this by today, just make sure that's turned in by Friday. Okay, you guys can turn this in definitely before you leave the weekend. Okay, and then the other thing today, last about 15 minutes or so, I'm gonna roll a Veritasium video on well, the title right now is how gravity actually works. It goes through a general relativity approach. Now he changes his titles because he's what gets the most clicks. The title of this video used to be "Gravity is not a force." So interesting perspective there. And so let's look at these relativity puzzles. In this equation bank, I gave you guys 4 equations. You have your 3 dilation equations, which is just this poster right here. You guys remember these dilations? We got for the twin paradox. You guys remember the twin paradox, rocket twin versus Earth twin? There's a time dilation. There's also a corresponding length contraction. Do you guys remember the train going through the tunnel? Okay, and there's also a momentum dilation that's going to show up. I also gave you guys mass energy equivalents. Do you guys see E equals mc squared? E equals mc squared, right there. So we're going to navigate that. That's the energy from nuclear reactions. Whenever there's a nuclear reaction, there's a difference in mass. You can convert that into energy. So by multiplying by the speed of light squared. Ooh. Okay. So here, I'm gonna walk you guys through these, read these with you. Some of these take some calculations, take some paper and a little bit of time. Some of these you might be able to answer fairly quickly. So, very first question. Earth twin stays on Earth, rocket twin flies around in a rocket close to the speed of light. Let's call that a relativistic speed. Ooh. And in this table, I gave you this from right to left, I gave you the speed of light, c equals 3 times 10 to the 8 meters per second. You know that. I gave you the speed of rocket twin's rocket. Now, everybody has a different paper, just like normal in this class. So everybody's rocket's a different speed. Mine says 2.1 times 10 to the 8 meters per second. That's about 2/3 the speed of light. Yours says something different. I also gave you an interval of time. No, you guys see it says T naught. That refers to rocket twins' passage of time. So mine says 24 hours. So my rocket twin would say, oh, I've been flying around for 24 hours at the speed. Right? But Earth twin says a different amount of time has passed. How much time? Can you guys navigate this expression right here and solve for Earth twins' passage of time relative to rocket twins' passage of time? You guys see that? Time dilation? Okay. That's number 1. Number 2. We're back to Earth twin and rocket twin. So we're sticking with the twin paradox scenario. Okay. This time, we're interested in this length contraction. So these 2 twins are disagreeing about the length of the rocket ship. Now, I gave you the rest length here. Now, my paper says 8 meters long. So when the rocket was on Earth, they both measured the rocket and said, yeah, we agree, it's 8 meters long, right? But when rocket twins rocket is flying at a relativistic speed, Earth twin is looking through a telescope and says, well, it looks like it's a lot shorter than that. My paper says 5 meters. Now, if you also know the speed of light, there is enough information there where you can calculate how fast the rocket is going. And that's this length contraction. Another context you guys saw this recently. You guys remember that train going through the tunnel? And was the train longer than the tunnel or shorter than the tunnel? It depends on whether or not you're riding along with the train, or if you're in an inertial frame of reference watching the train go through the mountain, say from side view, right? I should emphasize for all these expressions, like the time dilation and length contraction, you never notice anything strange in your own locality, in your own frame of reference. If you are along for the ride with rocket twin on the rocket, your own clock looks like it's beating 1 second per second. And if you measure the length of the ship, it's always the original length. It never changes. Right? But if these twins break out telescopes and they look at each other's clocks and each other's lengths, okay, only then do they notice something strange in the other frame of reference, right? So relative. Right, number 3, particle physicist accelerates particles in a synchrotron close to the speed of light. I've been promised you guys this question was going to come up. Here it is. So this is something that particle physicists see all the time over the Large Hadron Collider over in Switzerland. You guys go, CERN in Switzerland. And so they'll put in some initial mass of, say, hydrogen particles, and then they have to steer that with magnetic fields around a huge synchrotron, like in a circular pattern. Okay? But the faster they get those particles moving, it appears that there's more and more mass than there initially was. This is called momentum dilation. So they have to increase the magnetic field strength to account for that, okay? Because of special relativity. Now, most textbooks have the momentum version of this, which looks like this. Oh, now you guys probably want to use this. Well, it gave the mass version, which looks like this, right? So that might be easier to navigate for number 3. Can you guys navigate for that for number 3? In number 3, I told you the apparent mass that you'd be steering with magnets in the synchrotron. You guys have this Lorentz factor, 1 minus b squared over c squared. Can you guys solve for the rest mass of particles that was put in initially? Okay. It's one algebra step. You just cross multiply that Lorentz factor. You guys see that? Okay, so there's 1 through 3. Number 4, a given amount of mass is converted into energy by a nuclear reaction. How many joules of energy have been produced? So whatever mass I give you, let's say that is the difference in mass, or the converted mass, or if this is antimatter matter reaction, that could be the full mass. Okay? Can you guys apply E equals mc squared? So here's the energy you get out of a nuclear reaction. Here's the mass difference due to that nuclear reaction times the speed of light v squared. Okay. Oh, a question that came up earlier today. Guys, does the square apply to both the m and the c, or only the c? Yeah, only the c. Only the speed of light itself is being squared. Afterwards, you multiply by the mass, and that gives you how much energy you get out of a nuclear reaction. Okay. Now, how much energy are we talking about? An enormous amount of energy. Hold on to that thought, because in number 6 we're going to get to. We'll address that. Put that in context. Right? But number 5. Actually, let's look at the bottom paper. You guys see number 5 and number 12 are really similar questions. It says, where does time tick faster? But we got different scenarios going on. So number 5 is a special relativity question. You guys remember special relativity has to do with how does time change due to your motion. So I have here surface of Earth. We'll call that Earth twins frame of reference. And option B is in a spaceship moving near the speed of light. Oh, that could be rocket twins frame of reference, right? So three ways you can get this. You can either remember the twin paradox story. Right? But guys, when rocket twin came back to Earth, because both twins started off the same age, when rocket twin returned back to Earth after flying around for a while near the speed of light, his twin brother on Earth, the Earth twin, which twin was really old and had a gray beard? Was that Earth twin or rocket twin? It was Earth twin. Earth twin was really old man, had a gray beard, which means that more time had passed in Earth twin's frame of reference. So which time, therefore, would have to be ticking faster for that to happen. Right? Okay. Another way you can get the answer is you can look at this expression, this time dilation formula. It tells the same story. So rocket twin says some amount of time has passed. If you divide by this Lorentz factor, V is always between 0 and C. It can be as slow as V, but it can never quite reach C. Right? So this fraction will always be between 0 and 1. 1 minus that, same story, square root of that. Guys, this Lorentz factor is always bounded between 0 and 1. So if rocket twin says, oh, 3 hours have passed, if you divide by, say, 0.5, that's going to blow up to like 6 hours. Ooh, that'll tell you whose clock is ticking faster. So if they're looking at each other's clocks and telescopes, I think rocket twin's clock looks like it's going tick, tock, tick, tock. Okay. But rocket twin looking back at Earth twin's clock looks like it's going. That's all embedded in that formula right there. Okay, you guys get number 5? Okay. Now let's scoot straight over to number 12. You guys see number 12? Also asks where does time take faster, but this is a general relativity question. So this incorporates gravity. Do you guys remember the other day I played a GPS video for you guys, global positioning system, where you had all those GPS satellites, but their clocks, they have atomic clocks, and those clocks have to be adjusted to account for both special and general relativity, and there's actually competing effects, right? So, guys, does gravity slow down time? Do gravity fields slow down time? Yes, which means if there's more gravity, would time be ticking slower? So if the question is where is time ticking faster, isn't that where there would be a smaller gravity field? And can you guys compare your two answer choices, the Earth and the Moon, and figure it out from there? So you guys know where there's more gravity, it's going to slow down time. Therefore, where there's less gravity, time's ticking faster. Okay, can you guys put that together? Figure that out? All right. So top of the page, number 6. There's a whole story with this one. I want you guys to take all this math and put some context to it. So it's like this. You're a resident of a spaceship moving between stars in a galaxy. In order to sustain a decent standard of living, each resident on board consumes an average of 40 kilowatt hours of energy every day. Now, I got that number from somewhere. I looked that up on Google. That is the rate of energy usage living in a developed country. So we're in the States, that's a developed country. Same thing for Canada, Europe, Australia, Japan. Okay. Everybody in all those locations is using energy at approximately this rate. That's sitting in the stream right now, powering the lights and the air conditioning. That's you driving your car around town. Hey, how about all the food you consume? How did that get on the grocery store shelves? It had to be transported there. And first, it had to be grown on some farming field, agricultural process. Okay? How about all the clothes you're wearing? So here, let's just take this number, copy paste it, put it into space. All right, so great. So we keep using energy that way. Just sake of argument. If the ship's fuel storage contains the given amount of nuclear fuel per resident, let's say it's all converted to energy. Suppose it's a matter-antimatter reaction. Just make it simple. Okay. How long can the ship go before having to refuel? Now, everybody has a different amount of fuel. Mine says 0.01 kilograms. Now, guys, just for fun, what would that be in grams? Now, you guys know in your calculator, you're going to leave it as kilograms. But 0.01 kilograms, how many grams is that? How do you go from kilograms to grams? You multiply it by 1,000, which is how many decimal places? 3. So wouldn't 0.01 kilograms be 10 grams? So my paper says 10 grams. No, of course, the kilogram number goes in the calculator, right? But for context, that is your smallest lab mass, your smallest lab weight. You guys see this right here? Hold it right here. Suppose I had this in my pocket. I might even forget about it. I might not even know this was in my pocket. It's so small. Right. Now, what if I did a matter-antimatter reaction? I converted this completely into energy. I used that energy at the rate that I'm using it as a citizen of a first world country. How long would that last for? Now, one thing I want you guys to see is that regardless of what the exact answer is, do you guys see your 4 multiple choice answers? They're all on the order of magnitude of thousands of years. Does everybody see thousands of years? Right. So that's the story I want you guys to connect. Is that when you run this expression right here, E equals mc squared, you plug in even just a few grams that you just hold in your pocket and not even know is in your pocket. Right? The amount of energy that comes out of that could power your life for thousands of years. So that's the context behind this. Okay? So you do have to run E equals mc squared. You'll get an enormous number of joules. But the other part of the story is you have to run this dimensional analysis table to convert to how many years would that last. Now, I should tell you guys, I don't remember why I did this, but whatever. I did accidentally leave off part of the table. So if you run the table as it's printed in front of you, as it's photocopied, it only gives you the number of days. Guys, if you want to go from days to years, you have to divide by what? 365, right? And then also looking at the numbers and how they panned out earlier today. I think in Excel, I actually plugged in 365.25. But whether you use that or 365, it doesn't really matter because it's just a rounding error, right? You're going to get something extremely close to one of these 4 answer choices, right? So you guys good? That's good? You guys can solve that one? Right. Number 7, as you speed up and approach the speed of light, your length is seen by a non-accelerating observer. Well, there's a few ways you can get this one. The answer is embedded in number 2. You guys see this table of values in number 2? So about the rocket getting, what, longer or shorter? Right. Or you can navigate this expression. You guys remember this Lorentz factor is always bounded between 0 and 1. So let's call it 0.5. If you have some initial length, you multiply by 0.5, are you getting longer or shorter? And I could also make a graph out of that. I haven't made the graph, but I should do that for the next edition of the book of posters. All right, number 8, as you speed up and approach the speed of light, your mass is seen by a non-accelerating observer. Okay, so you could navigate this momentum dilation formula. Or here's the graph version of this. I really like the graph version because I think the answer pops out really clearly here. Okay? So what happens to your momentum? Now, if you look at Newtonian momentum, we'll call it like the baseline value. That's this green dash line. Okay? But Einstein says, well, as you approach the speed of light, you actually follow this red curve. Do you guys see this red curve heads up toward what? Infinity. Aha. You guys see that? Oh, number 9. In a nuclear reaction, which of the following takes place? And something is being converted into energy. So, do you know how to interpret this expression? Because what's being converted into energy? Aha! All right, so you guys know what that M stands for, right? Right, because that's the answer to number 9. All right. Number 10 and 11, you might have reversed. I don't know, just however I put this together back in the day. So one of them, you're navigating a mass dilation, and one of these you're navigating a time dilation. Right. Now I'm just going to do the order that's on my paper, but careful. Number 10, number 11, you might have reversed. So in the mass dilation expression, or momentum dilation, if it turns out, right? What happens to m as v approaches 3 times 10 to the 8 meters per second? Oh, well, we just answered that. So as you approach the speed of light, your momentum approaches what again? Infinity. You can see that there, right? Or if you navigate the formula, if you like the algebra version of this, the formula version, what happens when you plug in c for this v? Guys, what is c squared over c squared? 1. What's 1 minus 1? What's the square root of 0? 0, right? Guys, suppose your rest mass was like, 60 kilograms. If you divide by 0, aha, and don't say 0 because the answer is not 0, right? Right. Yeah. All right, and now my number 11, which may or may not be your number 10, we got time dilation. It says solve for t when v equals about 0 meters per second. Ooh, that's a non-relativistic speed, right? So here, a couple of perspectives. One is you just plug it in and see what happens. So what happens when you plug in either 0 or just some non-relativistic speed for v? Guess what is 0 squared divided by c squared? What's 1 minus 0? What's the square root of 1? Right? Okay. Now, you guys know T naught and T refers to rocket twin and Earth twin's frame of time, right? Their frame of reference for time. Suppose rocket twin said, 3 hours have passed, and you divide by 1. That gives you what for Earth twin's time? Right? Right? Or in general, any rocket twin time divided by 1. Do you guys see the general answer to that question? Right? Do you guys see where I'm heading with this? Right? And there's a physics principle that I'm trying to get at here, and I'll spell it out for you guys. It's called the correspondence principle. Right. There's a story that goes with it. It goes like this. If you come up with a new theory of how something's supposed to work, then this new theory should do 2 things. It should be able to make testable predictions that the old theory was not sufficient at explaining. Okay. So think like GPS, you have to adjust the atomic clocks according to relativity. So that'd be a testable prediction. Okay. But also, your new theory has to be able to cover the basis that the old theory was perfectly fine at explaining. So when Einstein published his special relativity in 1905, right, not only does it have to be able to explain things that Newton couldn't explain, but it should also be perfectly consistent with Newtonian mechanics. And Isaac Newton, according to Newtonian mechanics, which we've been using from August up until, well, this week, right? Everybody's time beats the same. Only when you get to Einstein do you realize that time is actually fluid and beats differently, takes differently depending on your frame of reference, right? Newton said time is the same for everybody, right? So non-relativistic speed. Guys, if you hop in your car and you're driving along I-95 at 70 miles an hour, isn't that tiny compared to the speed of light? Yeah, in fact, this fraction is still extremely close to 0, so you can call it 0. Okay. So when you drive all the way to Merritt Island and back, and you're comparing the time on your watch to the time on your friend's watch, is everybody's time approximately the same time? Okay. That's the correspondence principle. So these equations are perfectly safe at non-relativistic speeds. They very simply simplify to Newtonian mechanics. Okay. And I think that's it. Right, guys, is that the whole thing? So I will leave this up for most of the rest of the class because that's a pretty useful poster today. If you need any of the other posters, they're hanging up around my ceiling. And again, the last about 15 minutes of class, I'm gonna roll a Veritasium video for you guys on general relativity. Right, if you need help, any questions, let me know. I can walk around and help you guys out. If you finish this by the end of class, which you probably will, turn to the grade tray, I'll score that for you. If you don't quite finish, then just make sure you have it by Friday.